Welcome to this lecture series in group theory. In this lecture, we'll look at a very nice application of Sylow theory, and we will show that any finite abelian group can be written as the product of its Sylow p subgroups. And that's a very useful fact in general about abelian groups. We will see a nice corollary of it also. Okay, so we have a finite abelian group, and let us recall just one fact, that if we have a finite abelian group, then for any prime p, G has a unique Sylow p subgroup. This uniqueness just comes from the fact that any two Sylow p subgroups are conjugate, and in an abelian group, two conjugate subgroups are actually equal because of commutativity of the group. Here are some problems for practice. And now let us get started. So this is the main theorem. We start with any finite abelian group. Then we claim that G is isomorphic to the direct product of its Sylow subgroups. So collect all the non-trivial Sylow subgroups for varying primes p, and then take the direct product. Then this product group is isomorphic to the original group. All right, so let's get started. So let mod G be equal to p1 to the power k1. Sorry, let's say a1, pk to the power ak. Where of course p1 up to pk are distinct primes, and each ai is a positive integer. I'm not writing that. And let gi be the and I use the because of the uniqueness, so be the Sylow pi subgroup of G. This is not aligned. Let gi be the Sylow pi subgroup of G. Right, so we want to produce an isomorphism between the product of all the gi's and the group G. So define a map phi from the product of gi's to the group G as phi g1 up to gk maps to the product. So this is just the product of the gi's taken in the group G. All right. So then one can check that this is a group homomorphism. So check that phi is a group homomorphism. And this happens because of the abelianness of G. In general, such a thing is not going to be a homomorphism. The abelianness makes it a homomorphism. So I leave this step. And now we will check the kernel. Once we show that the kernel of this map is trivial, then this map would be a bijection, simply because we are dealing with finite groups, and you just make a size comparison and you'll see that this would be then a bijection, because trivial kernel means injection, and since this and this have the same size, it would also be a bijection and hence an isomorphism. So okay, so we want to show that we will show that kernel phi is trivial. All right, so let's say this thing is in the kernel of phi for some g1 up to gk. Then by definition this is equal to identity, which means this product is identity, which implies gk is equal to g1 inverse dot gk minus 1 inverse. Right, so here we have already used abelianness, because I should be writing it in reverse order, but since the group is abelian, it doesn't matter in which order I write. So this implies that order of g to the k is equal to order of that, but order of gk divides pk to the power ak. Why is that? Gk is an element of g sub k, and the order of gk is pk to the power ak, and hence order of gk should divide the cardinality of gk, which just immediately implies that. And order of this divides p1 to the power a1 dot 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 pk minus 1 to the power a k minus 1. So why is that? Basically, order of g1 divides that, order of g2 divides the second one, and so on. Order of this guy divides that. Now, since the group is abelian, this means that if we raise this guy to this power, we will get the identity, and hence the order of this guy divides that thing, right? So abelianness is crucial for this implication. And since this and that are relatively prime, this forces that gk is equal to identity. So this forces that gk is identity. Because if gk were not identity, then this would be some non-trivial power of pk, and that would contradict the fact that this is equal to that, because the non-trivial power of pk cannot be equal to some product of some powers of things which do not feature pk at all. So this forces gk is equal to identity, and similarly you can show that each gi is identity. So basically this proves, there are some more steps to do, but this basically proves that kernel phi is identity, and therefore this is an isomorphism. All right, so that's the proof of this decomposition theorem, and this has a corollary that if we have a finite abelian group and n is some positive integer such that the order of the group is divisible by n, then G has a subgroup of order n. So this kind of thing is not true for general groups, but this is the converse of the Lagrange theorem, and this is sort of a converse to Lagrange's theorem, and this is true for abelian groups. And basically just use the previous theorem. First assume that G is a P group and prove it, and then once you have proven it for P groups, for which we have proven it for general, if G were a P group, then without the abelianness assumption this was true. We have seen that. And yeah, so just use the previous theorem from that point on. So I'll leave the details of this. And with that, I want to end this. As usual, like, comment, share, subscribe. I also have Patreon. The link is in the description below. Thank you for listening, and I'll see you next time.